This video is the second of two parts describing procedures in Statgraphics version 20 for performing accelerated life tests. Accelerated life tests are designed to estimate the failure time distribution of products that have lifetimes that are too long to estimate under normal usage. The products are subjected to higher than normal levels of stress using one or more accelerating factors, such as pressure or temperature. The results are then extrapolated to normal operating conditions using models such as the Arrhenius model. Version 20 has two procedures for estimating failure times. The first is the accelerated life test plots procedure. This fits models to estimated statistics obtained at several levels of an accelerating factor. Common statistics are the mean time to failure or a selected percentile of the estimated failure time distribution. Part 1 of these videos described the accelerated life test plots. This part describes the accelerated life testing procedure. This procedure fits models to observed or censored failure times at selected levels of one or more accelerating factors. It supports any of 7 failure time distributions. As an example, I'm going to consider data from an accelerated life test. Here, 25 items were tested at different levels of temperature and voltage. The length of time until the item failed was measured and recorded in a column here called hours, unless the item had not failed by 500 hours, in which case the test was stopped. There are two ways that the data can be entered into the accelerated life test procedure. The first is by defining two columns, one with hours, another with a censoring indicator. For example, here we have certain items that failed prior to 500 items. The actual failure times are recorded, and the censoring indicator is set to 0. On the other hand, if the item had not failed by 500 hours, hours contains 500, and the censored column contains a 1. Instead of specifying these two columns, we could have used instead a special column type called censored numeric. In that particular type of column, you can enter values such as greater than 500 to indicate if a value was censored. The approach used by the accelerated life testing procedure is shown here. First, we'll select a failure time model, such as the Arrhenius model, for data at different levels of a primary accelerating factor. The primary factor must be quantitative, such as temperature. We'll then add additional factors as linear components of the model. The additional factors may be either quantitative or categorical. Thirdly, we'll specify an error distribution, such as the Weibull distribution, to model the failure times at a particular combination of the accelerating factors. Finally, we'll fit the model and estimate the mean time to failure or a specified percentile at normal operating conditions. I've loaded the sample data into the Statgraphics version 20 data book. To run the accelerated life test procedure, I'll go to Relate on the top menu, go to the section on Life Data, and select Accelerated Life Testing. On the Data Input dialog box, I'll start by specifying hours as the dependent variable. The censoring indicators are in the column called Censored. In the field for quantitative factors, I first need to specify the primary accelerating factor, which is temperature. I can then add additional factors if I like, and in this case, I'll add voltage. When I press OK, I'll see options for the accelerated life testing procedure. There are 6 different models that I could fit, and 7 possible failure time distributions. Now, not every combination of models and distributions is possible. If, for example, I've selected a linear model, then I'd have different choices than if I selected an Arrhenius model. In the field labeled confidence level, I'll indicate that I want 95% confidence intervals. And I'm also going to check the box that says convert X from C to Kelvin. That's because my temperatures are in Celsius, whereas the Arrhenius model typically expects degrees Kelvin. When I press OK, I'll next be shown a list of tables and graphs. I'm going to select just the analysis summary and the plot of the fitted model for now. When I press OK, an analysis window will appear with the results. Let's take a look at some of the output generated by this procedure. First, this is the analysis summary. It shows that we had 20 uncensored values and 5 right-censored values. The accelerating model we selected was the Arrhenius model. The failure time distribution was the Weibull. In this particular model, there were 4 unknown parameters: the log of A, a coefficient on temperature, a coefficient on voltage, and sigma, which is related to the Weibull distribution. You see the estimates of the coefficients, you see the standard errors, and 95% confidence limits for each of those coefficients. Here I've written out the estimated accelerating model. In this model, log of hours is expressed as a constant plus a function of temperature plus a function of voltage. You also see likelihood ratio tests for the coefficients involving temperature and voltage. Because both p-values are very small, both temperature and voltage have a statistically significant effect on the log of hours. Here you see a plot of the fitted Weibull percentiles as a function of temperature with voltage set to 4. There are 3 lines, one for the 10th percentile, one for the 50th percentile, and one for the 90th percentile. At the normal operating temperature of 25 degrees, the 50th percentile is about 43,000 hours. We can take that same percentile plot and re-express it as a trellis plot. In a trellis plot, we show that same plot at various levels of a second factor, in this case voltage. You see plots at 2 volts, 3 volts, 4 volts, 5 volts, 6 volts, and 7 volts. It's quite obvious that as the voltage increases, the percentiles get smaller. We can also generate a table of predictions at a selected combination of the accelerating factors. Here you see a table for the normal operating conditions, which are 25 degrees and 4 volts. The mean time to failure at that combination is 42,602. and you can see a table of different percentiles. Also shown for both the mean time to failure and the percentiles are 95% confidence limits. Another way of looking at the failure time distribution that's widely used is to look at the survivor plot. The survivor plot shows the probability that a unit will still be operating after a certain number of hours. I've displayed it here at the normal operating conditions. The blue line is the best estimate of the survivor function. The red line shows upper and lower 95% limits. The accelerated life test procedure will also plot the failure time distribution at any combination of the accelerating factors. Here I've plotted it at normal operating conditions. You see the estimated density function. You'll also see vertical lines at the 10th, 50th, and 90th percentiles. There's also a marker at the mean time to failure, which is 42,602 hours. Finally, I can plot the residuals on a probability plot. In this case, it would be a Weibull probability plot. If the accelerating model and selected failure time distribution performed well, the points should fall approximately along a straight line on this plot. They're not bad in this case, although there may be some slight deviations from the assumed model. For more information, please visit www.statgraphics.com.